Okay, so from F equals ma, we showed way back in introductory physics that if we integrate this side over the distance traveled by the object, we get something that we call the kinetic energy, T or K. And if we integrate this over the same distance the particle travels, well, that's defined as the work, and it's the difference in potential energy, or minus that difference. We have another scalar function. So these are scalar functions, potential energy and kinetic energy. And in the last video, we showed that we sort of motivated that very abstract idea that if we take the difference T or K minus U and we integrate that in time, as the particle, say, falls from some height, so we integrate from the initial time T0 to the time it hits the floor or something, Tf, T floor, T final, whatever, this quantity seemed to be smaller than other quantities such as, I don't know, U minus T or U plus T, right? U plus T is the total energy which is conserved, and that's always a positive quantity. So when you integrate that over the time, that's clearly a positive thing. It's larger than this thing. So it looks like this kind of quantity is minimized. And so we want to sort of generalize this idea. So we want to sort of start in an more general, sort of abstract way. Right? So this could be the height of the object. The object starts at some height, and over time, if this is time, it comes down, something like that. That's the path that the object follows. We want to think of other paths that the object could follow and see the ones that are associated with the thing that is smallest or that minimizes this kind of function, but we want to be more general. So we want to consider some other function like that, some other path, actually. So to be more general, we say, y equals some y of x plus some alpha b of x, where this thing accounts for the difference in the path, right? So to be specific for our case, if this is a time, then this path would be equal to saying, would amount to saying that the object is at different heights as a function of time, and that would not satisfy these laws. So we imagine constructing or inventing this kind of object where a more general expression would be in terms of x1 to x2. So this is an x1, this is an x2, or an x initial, an x final. We have some function, right? In this case, this is a function of the height, y, and this is a function of the derivative in y in time, in this case with respect to x, so y prime. And we integrate this kind of thing in x, or in our specific case in time. But the endpoints are the same, so this function b of x1 or rather beta equals beta of x2 equals 0. And so now we can ask what are the conditions on this general quantity such that it is a minimum, right? So we'll end up back at this place, going the other way. So we ask for how that thing varies with respect to this parameter. And so we're doing this calculation, x1 to x2 of this function, y prime, in dx. And we then apply the chain rule. We get dg by dy, dy by d alpha, dg by dy prime, dy prime by d alpha in dx. And we know that dy by d alpha is equal to beta, dy prime by d alpha is equal to beta prime, and so this becomes x1 to x2 of dg y beta plus dg by dy prime beta prime in dx in this general approach, and we get terms like dg by dy beta in dx, and then the next term we can do by parts, and so we'll break that up. The first term is that with beta, and we evaluate from x1 to x2. That's 0 because of this condition. And then we have minus x1 to x2 of what remains of this, which is by parts, we have beta d by dx of dg by dy prime in dx. And so we have what's left is x1 to x2 of dg by dy beta minus d by dx dg by dy prime beta in dx, and this has to be equal to 0. And so that's our condition, right? dg by dy minus d by dx dg by dy prime equals 0 is the condition for this thing, x1 to x2 g dx, to be a minimum. And so from the previous video, right, we can guess that the kinetic minus the potential, which we call the Lagrangian, or fancy L, if you will, that is the thing that minimizes this. And we can, in fact, see this if we evaluate dl by dy. Well, in this case, so this is time, sorry, this is y, but this is now fancy L, this is time, so this becomes d by dt of dl by dy prime. Well, given that x is time, we might as well call this y dot, right, dy by dt. And so we have that, let's see, we need to evaluate dl by dy, and that's going to be, well, we can do kinetic is equal to my dot squared over 2, and potential is equal to mgy, if we're thinking of an object that's falling under the gravitational force. That's the potential energy. And so we have that dl by dy is equal to minus mg, right? This difference here, the derivative of that with respect to y, we get a minus mg here. And d fancy L by dy dot is equal to my dot. And so when we do this, d by dt of dl by dy dot, we get m double dot. And so we see that these two things are equal to each other. Ma is equal to minus mg, the force, and so we recover, in fact, F equals ma, the vertical component of that, from this principle that T minus U, or kinetic energy minus potential, and dt is a minimum.